Nylon is perhaps the most ubiquitous synthetic polymer. It was first synthesized in 1935 and quickly found application after silk became scarce during World War II. The synthesis of nylon proceeds via step growth polymerization, alternating between two different monomers. These two reacting groups of monomers are carbon chains with compatible reactive groups on each side, in this case, sebacoyl chloride and diaminohexane. These two molecules happily react with one another, do a little electron musical chairs, and form a larger molecule called a dimer. This is the repeating unit of nylon 610, so called for the number of carbon atoms between the two functional groups. The chains must grow in steps. They can react with either single molecules, with other dimers, with other trimers, or even longer chains. Hence the name step growth polymerization. Compared to living polymerization, this is a more complicated process. In step growth polymerization, the initial quantity of the two reacting monomers is critically important. Too much of either results in early termination and, on average at least, shorter chains. In order to ensure long chains, we need a way to control the reaction. One such way is to tailor our monomers to be soluble in two different immiscible solvents. We first add a solution of diaminohexane. On top of this, we float sebacoyl chloride dissolved in hexane. Hexane, having a lower density than water, happily floats on top of our solution. In such a configuration, the two reactants cannot mix, and the reaction can therefore take place only at the liquid-liquid interface. Such a scheme is self-limiting. The interfacial reaction creates a polymer barrier which precludes any further reaction. Now, if we remove the polymer layer from the interface, the liquid-liquid interface reforms, and further polymerization takes place. This so-called rope trick can continue indefinitely until one of the reactants is exhausted. The advantage of this method of polymerizing nylon is that a 1-to-1 ratio of monomers at the reaction sites is maintained at all times. Having too much of either reactant only affects the total quantity of nylon we produce, and not the lengths of the chains themselves. It's also really cool and entrancing to watch. The disadvantage of this method is that it does not scale practically, it requires chlorinated reactants, and it depends on nasty organic compounds like hexane. One thing to note is that this is a condensation reaction, meaning that a small molecule of hydrochloric acid is released when the bonds form. In order to encourage further progress of this reaction, we need to remove this molecule. We can do so by adding a base to the diaminohexane solution, such that when the hydrochloric acid is produced, it gets neutralized in the presence of our base. And there you have it, the answer to the age-old question of how do I make nylon 610. Thanks for watching.